Thank you very much, Adi Jawad. Now we will the bending moment, as I told you, the bending moment, something maybe we don't need, we delete from here. I assume you are writing in your paper, right? You write down your paper so that you can see later on. So bending moment at point A is 0. Starting at the starting is 0. Of course, it's 0. Then what will be the bending moment here? If we go as I told you, we cannot see the slide. Why? I share it, right? I share it. I'm sorry, just wait a little bit. Something is why I shared this slide. Now you can see. Can you see now the screen? Hello? Can you see the screen? Hello? Yes. So see the reference line. This is the shear force diagram we did yesterday, right? Yeah, I have to start from the beginning now. So the shear force diagram we finished yesterday. You remember? Can you remember the shear force diagram? Yesterday we finished. Tell me please. Yes, you can remember. So we start it now. Now we know the bending moment diagram. Bending moment diagram is we start from 0, 0. This is the reference line. This is our reference line. Okay. Now at A, bending moment A, just left side at A equal to 0, because when we haven't start the bending moment diagram yet, so 0. Now from here to we go to this point, suppose point B up to here, how much? Up to here means up to I draw it for you again, and then bending, we have to draw the bending moment at each point, right? Now point B, at point B, our bending moment how much? Bending point B. So bending moment at B moment at B will be, so here is 0 plus or minus, doesn't matter. As I told you, the diagram of bending moment area, bending moment equal to area of shear force diagram. So if you want to find B, here or here, we don't know. We don't know in bottom or the top. We don't know. So area of the area is how much? We have the minus 1.167 into the distance is, we have how much? 1 meter. So we have minus 1.167 kilonewton meter. So it is minus, so it will be negative side. Minus 1.167 kilonewton meter is our bending moment diagram at point B. Now what will happen at we have point E here, some point, then what is bending moment there? So at point E, so bending moment at point E is, we have minus 1.167, and then we have this area. And how much the area? We have minus 9.167, up here. This the area showing in the blue diagram. So the height or depth is a minus 1.67 into width is 0.25 into 0.25. So, and do the calculation, how much it will be. Can you calculate the algebraic sum? How much it will be? Can you please? 9.167 into 0.25, it is 2.29. So minus 2.29. So this on this, if we do the algebraic sum, so minus 2.25 minus 1.167, right? 3 point how much? 46. 3 point equal to minus 3.4458, but we can write down 3.46. So here minus, so point E, so point E is there, even it still is minus, right? Minus 3.467 kilonewton per meter. Kilonewton, kilonewton meter. Then if you see the exactly at the B point, we have another external movement. Directly we have external movement. And how much this one? It is clockwise or anti-clockwise? It is the anti-clockwise. So we write down it is clockwise or anti-clockwise. It is see the clockwise, right? So clockwise. It is working. It is external movement is anti-clockwise. So externally it is producing, externally it is giving the clockwise movement, right? But when the body will want this, and it will have the opposite moment will create. So it will create the bending moment will create the plus, it is minus 20, but it will plus 20 in that case. So at E again, at its suppose at the right side, it was left side will be plus 20. So what will be happen? What will happen? So 3.467 equal to 20. So 16.4, 16.5. So equal to plus 16.5. Where at the same point at E. So here E and then 16.5, it is plus. So we will go plus 16.5. My drawing is not correct. I need to remove it. So here is the something new. That's why I have drawn the diagram, right? Here, so at the same point, at the last moment at the left side is moment 3.46, and we for external moment which is the clockwise, but bending moment will be internal will be anti-clockwise. So plus, that's why we write down here plus. And then after the algebraic sum, we got the plus 16. So plus 16 will be here to here, plus 16 point, sorry, now it will take 1 minute time. Plus 16.5 kilonewton meter, right? At the point. Now we go, we finish here. Now we will go to the point C. What is the point C? At point C, moment at C, again negative. Negative how much? Minus 17.16 into 0.75. Now if you do the algebraic sum, do it please the algebraic sum, you will find it will be how much? Can you calculate can you calculate? 7 point, it will be 7.67. So again it will be minus, it will be this is plus and this is minus, so plus. So if it is a plus 7 point, so it is 16.7 means here something lower than that, and then we connect it 7.67, right? Then still we go to this point where it will be moment D. At moment D, so at moment C it was plus 7.67. At moment D, MD will be, D point will be this area, right? This area is how much? 7.67 minus the 17. We are doing something wrong. 9 point, here is 9 point, not 17 point. Here is 9 point. Look, I repeat it from here. I repeat, the calculation is wrong, so I repeat from here. Moment at C, how much will be moment at C? So we have 16.5 here and 16.5 at this point, at this point. So we want to find the moment at point at C, or we can say moment C, little bit left side. So is equal to 16.5 we already have, and minus this is equal to actually straight line, and this 9 point minus 9.167 into the horizontal distance is from here to here is 0.75, the 0.75, so 0.75, so 0.75. So if you do the algebraic calculation, it will come, it should come, let me do it again. Let me do it 9.67, sorry, 9.67, 9.167 into 9.167 into 0.75, so 6.86, 6 point, this will come, this will calculate this one, only this part, minus 6.87. Now if these two do algebraic calculation, how much we should get? We get minus 6.867 minus 6.867, 16.5. We have 16.5 minus 6 point, how much? 6.67, right? So 9.87 something. Can you calculate and tell me the result? Correct result? 9.167 into 0.75, 6.87, you 16.5. So 9.626. Can you calculate, please? Tell me. I got here 9.67 or something, 9.16 and 9.62. 9.62. 16.5 minus 9.167 into 0.75. So 9.62. I got 9.62 here. So and the result is plus. The result is plus. So from here to here we will go. It is 16 and it's 9 point. It is 9 plus 9.62. Then here is 9.62. Then we are here now. After that, at moment at D again is minus the area. This area. I draw it again. This area. So height or depth is minus 17.167 into the distance is here 1. Distance is 1. So we will have result. We will have 9.67. It is the plus minus 17.167. So 7.54. We will have 7.54. So from where it is plus or minus, it will be minus. It is minus 7.54. And what is the point? MD, because it is the this is here, right? We go there. Now one thing remember, as I told you from beginning, if it is our slope in shear force slope is 0, like going horizontally, straight horizontally in bending moment, we will go inclined. Here going straight 0, so we'll go horizontally inclined. Here same, horizontally slope 0, we'll go inclined, and then here also slope 0, we'll go horizontally inclined horizontally, and the value is minus 7.54. Now at this point, now we will go to the point A, B, C, D, D, E, F. Just give some name to this point F. So at MF we already have minus 7.54 is there, and here the area is half. It is plus now. It is plus. So we write on the plus half the base is 1 meter and height is how much it was? 15. Height is 15. So we write 15. Okay, height was 15. So when you do the plus minus equal to, we will go minus 0.04, minus 0.04. Actually, we will assume it is almost zero. Almost, we will assume 0.04 is very small, so we will assume it is almost zero. Now from here to here, now previously this we go, the slope was zero, straight horizontal, so we go inclined. But here, if it is the, if the shear force diagram inclined, then we will go as a curve, and this is the curve like this. Okay, so it's zero. Now here this portion is negative, this portion is positive, and this portion is negative, and finally our bending moment diagram is drawn. Finish. Do you have any question? Tell me please. Someone has any question? Can you tell me please? Is anyone has any question? Hello, are you hearing me? Any question or clear? Clear, fine, it is clear. Now I try to show you something. Now here is the actual answer is given already. Maybe you can feel that this is very clumsy and very congested. The clear answer is there. Everything clear answer is there, right? Now we should show you something. I don't know what is the slide I was looking for. This slide I wanted to show you. Let me check. It's not working. Let me check. I wanted to show you something. Yes. Now, at the end of the, you go to the, at the end of the slide, I keep some practice problem and some information for you there, right? I keep you there. Here at the end of the slide. Slide is finished here. You see slide finish. Something there. Here is the definition of one thing in the for shear force definition. The resultant force, which is the upward direction and is towards the left side of the section, is positive shear. We already teach you this one. The resultant force, which is the downward and direction and the downward direction is toward the right hand side, the cross section is positive shear. Okay, so okay, then so this is we already teach you. Now some new thing I want to teach you. Now as I told you from where we got this information and how you know this, as I told you, we have drawn a shear force diagram for this beam, if you don't forget, like this. Okay, shear force diagram was like this, and bending moment diagram was like this. We have drawn it. Just now we have drawn a bending shear force diagram. How looks so like. We draw a shear force diagram, if you don't forget, like this, right? It was the shear force diagram. Just 2 minutes ago we have drawn a diagram, and then bending moment diagram was like this. Then I think this, and then this, then this, then like this, right? We have drawn the bending moment diagram. Now how? Now there is some rules. If load is like this, example of this one, then slope for shear force diagram is slope is constant. Go horizontally. So this is slope is constant, right? Constant slope, or even more clearly we can say zero slope. If there is load, is concentrated load, it is called, its name is concentrated load. This load is named concentrated load. This load is, sorry, this load is concentrated load at 10 kN. If concentrated load is there, so shear force diagram will be zero slope, like this. Okay. If shear force diagram is zero slope, the slope for the bending moment will be inclined, like this, linear, as I drawn here, linear. So more example. Here is the, here our load was like this, right? Our load was like this. So our shear force diagram was constant and zero slope, constant zero slope. And when the shear force is constant, we had inclined, linear slope, then here linear slope. When there is distributed load, we have distributed load here. In that case, our slope was linear, so we have drawn like this. Shear force was linear. But when shear force is linear, then our bending moment will be parabolic, and that's why we draw like this, right? Remember, we draw like this. Now, if our shear force diagram is our load diagram is like this, load diagram, the example I will show, if we have now, if the example for this one I have shown you, I didn't show you example for uniformly bearing load, but I will show you now after 1 or 2 minutes. If our load is like this, so shear force diagram will be parabolic. Shear force diagram will be like parabolic, right? Parabolic. And then the bending moment will be cubic, like this. And how it is, I will show in the example. But this is very important slide. Okay, very important slide. Keep remember. After that, here you have some work example is done. You can do at your home, right? And then you see the example is done. Okay, example is done. You can do at your home. Then another example is done here. You have the example there. Another example. These are very complicated. This is a complicated one. If you can do this, you'll be expert. So I will not show this one. We will have no time. But when you know the rules and regulation, then you can learn it, right? Then you can learn it. And then you go to the go back to the, we have 20 minutes time. I will try to show you this one. Okay, example 7.7 at your book. And then it's this kind of, you see that is a triangle. This is a triangular load. It is called the uniformly bearing load. The load name is uniformly varying load. Now, why uniformly varying load? You see, there is two support. This is the roller, and this is hinge. Now, at the support A and B, at A our load is 0. But as we going to the left side, right side to the B point B, our load is slowly increase up to here. It becomes 6 kN per meter at point B. So at B when we reach at B, our load is 6 kN per meter. At A, our load is 0. So from A to B, our load is increasing. But how it is increasing? Uniformly. Varying means vary. You know the meaning of vary? Varying means it is changing. So this changing is uniform. That's the name, uniformly varying load. And this uniformly varying load is a shape. Finally, it makes the shape triangular shape. Now, if it is the previously we learned that distributed load. Distributed load is like this. Distributed load is working like this, right? In the book, it show like this. Distributed load. It show like this. But when we write the hand, we show like this. Distributed load. So distributed load, as example, 6 kN per meter. That means this 60 kN per every meter. Everywhere is 6 kN per meter. And then total load. Suppose if I give that it is 10. Distance is 10, so total load will be 6 into 10. You already learned this, right? 60 kilonewton. And the total load will be working just at the middle, 60 kilonewton. In case of the distributed load, is named distributed load. and UDL, uniformly distributed load. This name, this load is this load, this kind and this kind name is uniformly distributed load. In short, UDL. UDL, uniformly distributed load, and uniformly distributed load. But here, this one is triangular load. Triangular load. Its name is uniformly varying load. Now, in case of the uniformly varying load, okay, this is the beam. In case of the uniformly varying load, the total load, where how much will be total load? This is total load will be total load will be half the base. In our example, this 9 meter, okay, 9 into height is 6 kilonewton per meter, so total load will be 27 kilonewton, right? Is that correct? 27 kilonewton. This is the load. So but where this load will work? Where? Can you tell me? Can you someone tell me where this load will work? In distributed load, it works at the middle, center of the diagram. Now for the triangular load, the total load will be working which point? Tell me someone, please. Give me answer. If you are with me, please tell me answer. Are you with me? Are you here? Anyone? Are we hearing me? Are you in the class? Shabab. If you're class, then why not answering me? Look, the force will be working at the center of the diagram, of triangle. And previously, I think we have, I don't know, we have teach you or we didn't teach you. I don't know. I cannot remember. Did we teach you the center of the triangle? Where center of the triangle? Please talk to me. No, maybe no, right? Maybe I will show you now. I will teach you now. The center of the triangle will be working here. Suppose this is the B, this is B, and this is D. Learn it now from me. It's very important. Here. So from okay, I draw it more clearly. Okay, I draw somewhere here. Okay, very important. But who is the Hussain Ali Alawi? You are answering me. You answer me first. This is the rectangle. Okay, this is the rectangle. Now this is B and this is D. Where will be the center? Tell me. Where will be the center? Tell me. Don't waste time. Tell me please, quick. In the middle. In the middle here. Fine. Middle. That means if we take the axis y-axis here, and it is the x-axis, so center will be the b by 2 and d by 2. Is that correct? Is that correct? Yes. is the d by 2, right? Here the center. Now here, if we draw a triangle, like this, okay, here is b and here is d. Sometimes we show by d or h, doesn't matter. Okay, the center will be here. Now if the center is there, here is center. Now remember, the center will be from this point, it's called base. This from this point, 1/3 of b, 1/3 of b, and from this point it will be 2/3 of b. Remember always. Okay, from bottom it is 1/3 of h height, and from the top it is 2/3 of h. Okay, center for triangle, okay, understand? Tell me or not. Tell me please, clear or not? Clear, right? Clear. Now in our example, our triangle was here, and it was 9 here. So our center will be working actually here. So from 1/3 of a 1/3, from the base 1/3. So here, from here to 1/3, you see, basically to 1/3. So 1/3 of 1/3 is 1/3 into 9 equal to 3, and here is 2/3 of 9 equal to 6. So our center will be working at 6 meter from here and 3 meter from there. Okay, clear now? And our total load will be working actually there, and total load is 27 kilonewton. Now clear what I want to tell you? Our total load will be working at this point, 27 kilonewton, and distance is from here to is 3 and here to here is 6. So total distance is 9. Now clear? Tell me quick. Tell me please. Very important. Clear? All right. Alright, okay. Now, here the example is in book is done, but to make it is more clear, I already put it here by handwriting. Okay, at your home you can check. Okay, so example 7.7, example 7.7, page 348. So now, so when you know the still, we didn't start, still here. Okay, still we have to work here, right? Now, how much the reaction force? First step is we need to calculate the reaction force here. Reaction force. Now, you are going to tell me what reaction force, right? It is that it was our triangle. 6 kilonewton per meter. We calculated it, and then we have two support is 9 meter apart, A and B, and we found the total load is 27 kilonewton. While we made the total 7 kilonewton, now you tell me what is the RAB. Calculate the RAB and tell me the result. Calculate the RBV and tell me the result. Here to here is 3 meter distance, here 6 meter distance, right? And here is 20 kilonewton. So tell me the calculate and tell me the reaction force. Okay, please tell me the reaction force. Did you calculate? Please tell me. Reaction force. Look, the reaction force is the simplest one and the fastest step in your shear force diagram. Now, if you cannot do it, you cannot do anything. So I suggest you learn it more carefully. Okay. So take the moment at A. Moment at A is take the anti-clockwise positive. If you take the moment at A, so RAV into 0 because it is going through the point. So what else we have? We have 27. 27 into distance is how much? 6, and it is rotating in clockwise, so minus. Then what is else we have? Remember when we the triangular load, when we convert to the total load, then only this load is we have only this load, right? 27, and this time we can forget the other triangular shape. So A and B are AB are A VB. That's all you have. So this is, you take the moment at A, so a moment at 0 minus 27 point into 6, and then RV we have, may we go, yes, still 2 minute time we have, plus RVV into 9 equal to 0. Now RVV equal to how much? Tell me please. 27 into 6 divided by 9. How much? The reaction force? I wanted to give you the attendance, but attendance is not working. So I'm sorry. It's still 2 minute time we have, so we finish this one and then we can move. 27 into 6 divided by 9, so 18. 18. So RVV into 18 kilonewton. If RVV is 80 kilonewton, summation of vertical force equal to 0. Take the positive. So RV it is. I have a class in the KFU. Yes, you can move you can move, no problem. You can go, no problem. So RAV plus minus 27 plus this is minus 27 minus 18 plus 18 equal to 0. So RAV equal to 9 kilonewton. 9 kilonewton. Okay. So reaction force, we got the reaction force. We got the reaction force here. RA is 9 kilonewton. RA is 9 kilonewton, and here is RB is 18 kilonewton, right? So we have 9 kilonewton here and 18 kilonewton is there. So our today time is finished. Today time is finished. So we'll start next class from here, and this will be the last one in our example. Okay. Do you have any question? Still is not working, so I cannot give you attendance. Maybe I will give you attendance to everyone. You have any question? Okay, fine. If you don't have any question, so we can finish here.